A switch can be constructed with any mechanism bringing two conductors into contact with each other in a controlled manner. This can be as simple as allowing two copper wires to touch each other by the motion of a lever, or by directly pushing two metal strips into contact with each other, like this old-fashioned knife switch. However, a good switch design must be rugged and reliable, and avoid presenting the operator with the possibility of electric shock. The conductive parts in a switch used to make and break the electrical connection are called contacts. Contacts are typically made of silver or silver-cadmium alloy whose conductive properties are not significantly compromised by surface corrosion or oxidation. Gold contacts exhibit the best corrosion resistance, but are limited in current capability and may cold weld if brought together with high mechanical force. Whatever the choice of metal, the switch contacts are guided by a mechanism ensuring the square and even contact for maximum reliability and minimum resistance. Contacts can be constructed to handle extremely large amounts of electric current, up to thousands of amps in some cases. The limiting factors for switch contact current capability are heat generated by the current through the metal contacts while closing, sparking caused when the contacts are opened and closed, and the voltage across the open switch contacts, the potential of current jumping across the gap. Smaller switches for lower current at lower voltages, like 120 volts and less, will use a single set of contacts, such as this single-pole, single-throw toggle wall switch. This single-pole, double-throw toggle switch also uses single contacts, but there are two sets of them. For voltages of 220 volts and above, for higher currents, a double contact such as this may be used. By using two contacts, the distance an arc must travel is doubled. When contacts are opened quickly at high voltage levels, a conductive metallic vapor can form that allows the current to continue traveling between the open contacts. This phenomenon, known as arcing, creates the greatest obstacle to circuit interruption. Unlike this welder, switches are designed to reduce or eliminate arcs because they quickly damage metal surfaces. High voltage switches have special arc suppression equipment. As an extreme example, here is a very large switch attempting to open three 230,000 volt power lines without arc suppression. Here is an even bigger switch trying to open a 500,000 volt circuit when the arc suppression system malfunctioned. Normally, large switches use some method of arc suppression. Medium and high voltage switches employ one of 4 different arc interruption technologies. All take advantage of the fact that even the most powerful AC currents pass through zero current levels twice each cycle. By reducing the amount of conductive gas between the contacts, the arc cannot be sustained when it passes through a zero current. Some large switches use the arc to generate a magnetic field that forces the arc into arc chutes, which lengthen and cool the arc, allowing it to extinguish at zero current. In some switches, the contacts are immersed in a container of non-conductive oil. When an overcurrent occurs, the arc heats the surrounding oil, forcing it to flow violently. The rapidly flowing oil displaces the arc gases and breaks the arc path. Some switch contacts are placed in a vacuum to avoid arcs. Sulfur hexafluoride, SF6, is an insulating gas used in large switches in 2 ways. In puffer designs, it blows across the contacts as they open to displace the arc gas. In blast designs, it's used at high pressures to open the contacts simultaneously, extinguishing the arc. SF6 gases are rated for the highest voltage of all breaker or switch designs. Both AC and DC contact arcing can be minimized with the addition of a snubber circuit, a capacitor and resistor wired in series in parallel with the contact. A sudden rise in voltage across the switch contact caused by the contact opening will be tempered by the capacitor's charging action. The use of snubbers in DC circuits is nothing new. Automobile manufacturers have been doing this for years in engine ignition systems. minimizing the arcing across the switch contact points in the distributor with a small capacitor called a condenser. As any mechanic will tell you, the service life of the distributor's points is directly related to how well the condenser is functioning. Arcs can be very dangerous. They create very bright ultraviolet light that burn the retina of the eye. Sometimes arcs create low resistive paths for electricity to flow between electrical conductors such as wire. This can create an explosion of superheated gas called an arc blast. An arc blast can be a powerful and very hot explosion capable of killing or injuring anyone nearby. Here is a clip of an arc blast created on purpose by shorting some high current 480 volt AC wires.
Okay, ready?
Thereby, roll.
Cameras ready?
Roll.
Here we go.
Whoa.
You certainly would not want to be close to something like that, so great caution is required measuring or working near high current and high voltage conductors. Special suits like this are used to protect technicians when they have to work on live circuits. This one was exposed to an arc blast. Switch contacts can be ruined by contamination. One major disadvantage of standard switch contacts is the exposure of the contacts to the surrounding atmosphere. In a nice, clean, controlled room environment, this is generally not a problem. However, most industrial environments are not this benign. The presence of corrosive chemicals in the air can cause contacts to deteriorate and fail prematurely. Even more troublesome is the possibility of regular contact sparking, causing flammable or explosive chemicals to ignite. When such environmental concerns exist, other types of contacts can be considered for small switches. These other types of contacts are sealed from contact with the outside air, and therefore do not suffer the same exposure problems that standard contacts do. Some switches are designed to be used in environments where there might be flammable gases. These are called explosion-proof switches. They use sealed contacts. A common type of sealed contact switch is the mercury switch. Mercury is a metallic element, liquid at room temperature. Being a metal, it possesses excellent conductive properties. Being a liquid, it can be brought into contact with metal probes to close a circuit inside a sealed chamber simply by tilting the chamber so that the probes make contact with the liquid metal. The mercury switch is tilted one way to close the contact and tilted another way to open the contact. Aside from the problems of tube breakage and spilling mercury, which is a toxic material, and susceptibility to vibration, these devices are an excellent alternative to open-air switch contacts wherever environmental exposure problems are a concern. Mercury switch contacts are impractical to build in large sizes, so you typically find such contacts rated at no more than a few amperes and no more than 120 volts. Another sealed contact type of switch is the magnetic reed switch. It is a pair of very thin magnetic metal strips or reeds which are brought into contact with each other by applying a strong magnetic field from a permanent magnet moved closer to or further away from the tube by an actuating mechanism. Due to the small size of the reeds, this type of contact is typically rated at lower currents and voltages than average mercury switches. However, reed switches typically handle vibration better than mercury contacts because there is no liquid inside the tube to splash around. A small amount of arcing is actually good for mechanical contacts as it helps to keep them clean from dirt and corrosion. Gold contacts are often used for small currents because it will not corrode. Thanks for watching.